Okay, it's 7 o'clock. We have these warm-up problems. I'm going to give a few minutes, see if a few more people join. Just go ahead and get started on these, and we'll talk about them in just a second. So the questions are asking if these sequences are monotonic and bounded. So if you're going to say monotonic, make sure you specify if it's increasing, it's decreasing. If it's not bounded, is it at least bounded from below or above? All right, so we can start talking about A here. So we've got the sequence n over n plus 1. The sequence goes from n equals 1 to infinity. So we note that the n's are always positive, right? So what does that mean about our sequence? Well, it's never going to be negative then, right? So we at least know that this quantity is always greater than 0. Now, on the other side, can we bound it from above? Well, as n keeps getting bigger and bigger and bigger, this thing is going to get closer and closer to 1, but never really get there, right? If you take the limit, you can kind of see that, right? Dominance of powers kind of thing going on. So this guy is bounded by 1. So we have a bound, so we know that this thing is at least bounded. But what about increasing, decreasing, monotonic? Well, what we can do is let's define a function, f of x, and write that as x over x plus 1. The derivative then is 1 over x plus 1 squared. And we'll note that no matter what x is, as long as this x is positive, well, even when it's negative, but at least we know that it's always positive. But this quantity is, in fact, always positive. So that means if the first derivative is always positive, then the original function is always increasing, meaning that our sequence is always increasing. So we now have that this guy is bounded, and monotonic. And we'll just kind of specify that it's increasing. So what about B? We've got this n cubed over n to the fourth plus 10,000. Yeah, we got 10,000. We're going from n equals 0 to infinity. And again, let's look at the boundedness. And we note, similar to A, that because n is going from 0 to infinity, it's either 0 or always positive, right? And that means that this quantity here is always going to be, it's got a lower bound, bounded from below. Now we've got this less than or equal, because it can be 0 at that first index, right? But what about above? Do we have any kind of bound from above? Well, we at least know that this guy's never going to get to 1, right? We go from 0, and then as soon as we plug in n equals 1, we got 1 over 10,001. And the bottom is always going to be way bigger than the top, right? As long as we're looking at these integers. So it might not get close to 1, but we can still bound it by 1, right? So we have a bound. We have a bound above and below. So we know that the sequence is at least bounded, right? But what about increasing and decreasing? Well, again, what we're going to do, I'm going to give myself a little bit more space here, is define this f of x, x cubed, make it a little bit bigger, x to the fourth plus 10,000. So my first derivative here is negative x squared minus the quantity x to the fourth minus 30,000 all over x to the fourth plus 10,000 squared. So you have a little bit of a messy first derivative. But if you look at it, we can't immediately tell if it's always positive or negative. So what we're going to do is, remember back from Calc 1, let's define fxc equals 0, or f prime of xc. So when is the first derivative 0? By a max or min extreme kind of deal, right? Well, this happens at 0. And you can note from the this quantity here, guy in pink, that we have plus or minus the fourth root of 30,000. Another root. So we don't have to worry about the negative one, right? Because we'll never be there. So let's kind of make a chart here. We're going from 0 to the fourth root of 30,000, and then we're still going on, right? We plug in just an arbitrary number. We can even plug in 1 here, and we can find out that this region is positive. And if we plug in another point from this other side, we get that this is negative. So what does that mean? That means that this thing is not always increasing or decreasing, right? And therefore, we can't say that it's monotonic. So we have bounded and not monotonic, right? So that wraps up our warm-up. So we're going to be talking about a new thing for a long time. so get used to them. I honestly think that this is the hardest part of Calc 2 is sums. You're going to learn a lot of different tests, and we're going to learn a few today. Maybe you've already looked at the book. If not, then we're going to kind of go over them. So sums. we've typically seen these sums written from maybe I equals 1 to n of some kind of sequence AI, right? And if we added these all up, we can write this as Sn, right? And if we write out what the summation form looks like, we got, A1 plus A2 plus A3, and this keeps adding until we get to AN. So it's kind of like a sequence, right? Where each one of these terms is defined by the sequence, but now we're adding them all up, right? So some of the same kind of rules apply to these things, and that's why we learn sequences first, so we can really dive into sums. And in fact, what we're going to do now is take the limit as this n approaches infinity of Sn, and common notation for this in summation form, so you put the infinity on the top here of AI, and we write that as just S, not Sn. So the Sn is what's called the partial sum. Right? It's not the total sum, it's only a certain amount, it's a finite sum. So if we take the limit as this n goes to infinity, we get the infinite sum, and what we call is S. Right? So if we have that the limit as n approaches infinity of Sn exists, n is real, then we have that the series is convergent. Right, and that makes sense. If we have this capital S without the n, just S, right? That means that the limit existed and it's a real number. If that's the case, then the sum, the infinite sum, is a real number. And like how we behaved with convergence and divergence in integrals, this is the same for sums, right? If it actually gets to a finite real number, it's convergent, right? If not, we have divergent. So what are some properties about convergent series? So let's assume that we've got some infinite series here. So if these are going to be infinite series here. So we have the sum of AN and the sum of BN. These guys are convergent. Then we've got some properties here. If we have the sum of C times AN, where C is just a number, just a constant, then this is equal to C on the outside of the sum. So basically, we've added up all these terms that have this multiple of C in them, and we've just factored it out. But we can only do that if the sum was convergent, right? Okay. Another property we have is that if we added or subtracted another sum that's convergent, then we can just add or subtract the sum of those sequences, or those terms. Note here that the indexes that we have on the top and bottom of these sums, those have to be equal. You can, of course, because they're adding things off, you can have some of those separate off to the side to make sure that you have the right indexes, but just make sure that the things in pink are the same. That way we can add them together. Now, This isn't dependent on if AN and BN are convergent, but this is another property that we have to kind of remember here, is the sum of AN times the sum of BN. This is not the sum of AN, BN, right? This doesn't just hold for infinite series, but finite as well. So just keep that in mind. The book likes to talk about it, so I think that's worth to kind of throw in here. I've seen kind of that mistake before. So let's go on to the next page. And we'll talk about our first kind of special series that the book likes to talk about, and I think it's pretty important. So we've got the geometric series. And what this is a sum that goes, A is a constant here, A plus AR plus AR squared plus AR cubed, and then we're going to keep increasing the power there, and it goes on forever, right? Writing this out in our summation notation, we have n equals 1 to infinity of AR the n minus 1. So this is one of the few series that you'll actually find out what this is equal to, right? So most of the time when you're asked to find if a series is convergent or divergent, you won't typically find what it converges to if it does converge. It's a lot harder to do that kind of thing with sums than it is integrals. So this is one of the few cases that we can actually find it out. And this is how we do it. So it starts by writing a finite sum, so that's nn, it's partial sum, right? And A plus AR plus AR squared, and we keep going until we get to the term AR n minus 1. Now, if I multiply this same line by R, so R times Sn, this guy is equal to, so now the first term is AR, right? So I'm actually going to move it right here so you can start to see a pattern because they all increase their power by 1. I'm going to get AR n minus 1, and then I'm going to have an additional term right here, which is ARN. If I subtract these two things, right, so I have that Sn minus RSn, there's two terms that survive, right? The A, this guy here, and then this term here are the only two that aren't shared by this thing. So A R to the n. So I can solve for Sn now. Solving for Sn, I find that I get A times the quantity 1 minus R to the n all over 1 minus R. I can actually take the limit of this guy, right? The limit as n approaches infinity of Sn. This is equal to, it's A over 1 minus R, as long as we have that R is bounded between -1 and 1. Otherwise, this diverges. And you can kind of see that if you do have a limit, and this is actually in the book as well, so take a look at that. So that leads us to our first practice problem for sums, number 2 here. So we have the sum n equals 1 to infinity of just n. So go ahead and think about this just a second, and then we'll kind of go over it, find out if it converges, diverges. See if you can actually find out what it converges to, if it does converge. So this actually goes off to infinity, and this actually diverges. So yeah, let's kind of look at it here and do it in a more like formal sense, right? So we always want to do our problems pretty formally. So we're going to write our Sn here. I'm going to write capital N so that we don't mix up our lowercase n's. And so this goes from lowercase n equals 1 to capital N of n. And we know what this partial sum is, back from Calc 1. It's this guy, right? So now, if we take the limit, capital N goes to infinity, you can see that this guy goes off to infinity. So this sum diverges. And if you think about it, it makes total sense. If I add 1 plus 2 plus 3 plus 4, and that thing keeps growing, and I keep adding more and more positive numbers that are growing, that thing is going to blow up. All right, so that diverges. So make sure that we put diverge, divergent. So that leads us to our next practice problem, 3 here. And it's the sum, n equals 0 to infinity of -1 to the n. So go ahead and think about that for a second. This one's a little bit, it's not as straightforward. A hint, you can utilize sequences to determine if it's convergent or divergent. Okay, so if we start to list the partial sums here, so I'm going to write S0. The first term that we get is 1. The next term is, so this 1, now we're adding a -1, right? So we get a 0 here. The next one we get as a 1, and then it goes back and forth between 0 and 1, because we're always adding 1 and then subtracting 1, right? So we can consider this partial sum as a sequence, right? The sequence of Sn. And what happens to the sequence? Well, we kind of remember what that sequence was doing back in the other section. If it's going back between 0 and 1, 0 and 1, 0 and 1, and you're right, it's not monotonic, right? So this sequence is not monotonic, and that means even though it's bounded, this thing doesn't converge. So if the sequence of these partial sums is not converging, then the sum itself is divergent, right? So this guy is divergent. So it's weird to think that this guy isn't going off to infinity or negative infinity, but it's still divergent, right? Because it actually doesn't get to something. And that's what convergent means, that it gets to some number, right? This just keeps going back and forth, right? So now this brings us to a pretty good point. If the sum n equals 1 to infinity, that's like a weird infinity, there we go, is convergent, then the limit n approaches infinity of an equals 0. And that makes a lot of sense. So there's a question about S1 and S3 being -1. So if you look at the sequence, so this an, it would go back between 1 and -1, right? But now remember, we're adding them. So we're doing something like this. So the first term is just this 1. The second term is 1 minus 1. This next term is 1 minus 1 plus 1. And then, of course, we're going to get that. All right. So those guys are going to cancel out. So we go between 1 and 0. So going back to this limit here. So we actually now see, I have a pointer now, and I just found out that I had this pointer. That's going to be real helpful. Otherwise, I was like moving around the screen without actually pointing at anything. So yeah, so we're going to talk about, this makes a lot of sense compared to when this is convergent. So now make sure that we understand the order here. If this guy is convergent, then we have this limit, right? So if we have this limit, doesn't necessarily mean that this is convergent. This is a one-way condition, right? And that's really important to remember, not to flip-flop these. So if an is convergent, that means that this, adding all these terms together, we get a finite number, then it makes sense that things keep getting smaller and smaller individually, right? So my an is going to 0. Because if it's not, then I'm going to keep adding something that's not getting to 0. It's not getting smaller. And if that's true, then I'm going to be blowing up when I add them all together, right? So that leads us to our first test. So we have test for divergence. I'm going to go ahead and box this guy. Right? This is our first test for sums. And what it is here, if the limit as n goes to infinity of an does not exist, or it's not equal to 0, then the sum, the infinite sum of an is divergent. So this is also really important to remember the ordering of. And what this actually means. If the limit as n goes to infinity of an does not exist, or it's not equal to 0, then the infinite sum is divergent. This statement says nothing about convergence. Remember that. It's the test for divergence, right? So let's say I have that the limit as n approaches infinity of an is equal to 0, which brings us back to up here, right? Remember that I said this is only one way. Just because this is true does not mean it's convergent. So this is accurately named. It's a test for divergence. This tells us nothing about convergence. So just kind of remember that. That's one of some of the big mistakes that I see when first learning some of the tests, is applying this in the wrong direction. All right, so this brings us to our next practice. You can kind of guess what we're going to apply to this one. So we've got the sum as n equals 0 to infinity for n squared minus n to the third, 10 plus 2n to the third. So does this converge? Does this diverge? Give it a go. We'll talk about it in just a second. All right, so let's apply the test for divergence on this guy. So we're going to say that the limit as n goes to infinity of 4n squared minus n to the third over 10 plus 2n to the third. This is going to be equal to the limit as n approaches infinity. So we're going to factor out a 1 over n cubed on the top and the bottom, and we're going to cancel. So then we've got 4 over n minus 1, and bottom 10 over n cubed plus 2. The 4 over n and the 10 over n cubed go to 0. This guy is equal to -1. This is not equal to 0. So for our test for divergence, this guy, this whole sum, diverges. Now, this next thing is very important by divergence test. Make sure anytime you're proving that a sum is divergent or convergent, that you say by some test, right? And we're going to learn a little bit more about some other tests later on. So this is our first test for divergence. Now, so we're going to list it. The next one we're going to kind of learn brings us to a good point. So we were spending all this time with integrals, right? The whole first half of this course is integrals, right? We're learning about new integration techniques, integration by parts, trig substitution, partial fractions. So why don't we kind of utilize all this knowledge that we know about integrals? We were using sums to approximate integrals, right? So why can't we do the opposite? Why can't we talk about what happens if we approximate a sum using an integral? So let's kind of draw a little chart here. If I have a function, kind of like that, and I'll actually give this guy definition, I'll say that it's equal to 1 over x squared, then let's say I wanted to take a sum that's the sum n equals 1 to infinity, 1 over n squared. So the first term of this is going to be 1. And what that means is if we start here at 1, this is a pretty bad picture, but this guy has an area of 1. Right? And then we have all these other tick marks. We go up, draw another box. Right? So now this is our infinite sum, all those squares being added together. But what we're doing is if we look at an integral, this green segment, we can almost approximate what this sum is. So we might not get what the sum is going to exactly, but we can kind of tell, right? And by that, we can determine if it's convergent or divergent. So this is less than the sum from 1 to infinity of 1 over x squared dx. And then because I started at 1 here, back over here, right? And then I had this extra square, I have to add this 1 term. Right? And on the right-hand side of this inequality, we remember from a previous section that this integral is actually 1. So this whole thing, that sum is less than 2. So fun fact is that you don't have to remember this, that the sum n equals 1 to infinity, 1 over n squared is equal to pi squared over 6. That's a really weird concept. And, hopefully maybe you guys will get interested and see how this is proven. But this is a pretty cool thing, like, right? Pi showing up in a really weird place here. So let's go to the next page and talk about the next big test, the integral test. Let's go ahead and box this guy. The integral test. And what is the integral test? Well, we've got that the integral from 1 to infinity of f of x dx. If this guy is convergent, this guy converges, then we have that the sum, of n equals 1 to infinity of an converges. Now, this also, so if we have the same integral and this diverges, then we have that this sum diverges. So that's pretty nice, right? If we can show that the integral of the equivalent thing that's inside the sum, if that whole integral is convergent, then we know that the sum is convergent. And if we know that that integral diverges, then we know that the sum diverges. So that's a lot easier to kind of prove convergence and divergence for sums because we're a lot more familiar with taking integrals, right? So that brings us to our next practice problem. So we have 5. And it is the sum n equals 2 to infinity 1 over n times the natural log of n. And you can probably guess what you got to do to this, apply the integral test. So take a minute, see if you can figure it out. All right, so let's talk about 5 here. Let's define our f of x to being 1 over x natural log of x. And that means that we've got this integral here. Note that our sum goes from 2 to infinity. Right? So our integral here should do the same. Goes to 2 to infinity, 1 over x natural log of x dx. So this is an improper integral, so remember the first thing we got to do is write the limit. Now we can start to do the integral. You choose u equal natural log of x. We're going to get that du is 1 over x dx, and luckily we've got that. So this is going to bring us to, after performing the u substitution, we've got that the limit as b goes to infinity of the natural log of x from 2 to b. Now, this is the limit as b goes to infinity. Natural log of b minus the natural log of 2. And this goes to infinity. So we know that this whole sum diverges. And I've got to write that here. So this diverges by integral test. And again, the fact that I write by the integral test is really important. So always list what test you're using. Let's go on to our next example here. We've got 6, which is the sum, n equals 0 to infinity of n e negative n squared. Take a second and see if this guy converges or diverges. We'll talk about it. All right, so let's talk about number 6 here. So let's define our f of x being x e to the negative x squared. Now we've got our integral going from 0 to infinity of x e to the negative x squared dx. And again, we've got an improper integral. First thing we got to do is write out our limit. Yep. This b goes to infinity of the integral from 0 to b of x e to the negative x squared dx. And this is another u substitution. If we do u is equal to negative x squared. And we have that du equal to negative 2x dx. So doing that out, once we do our u substitution, we get that this is the limit as b goes to infinity of negative 1/2 e to negative x squared, evaluated from 0 to b. This is equal to the limit as b goes to infinity, negative 1/2 e minus b squared plus 1/2. This guy is equal to 1/2. So we've got a finite thing, and that means that the sum converges. So we know that the integral converges, so we know that the sum converges. So converges by integral test. So these are our two examples for the integral test. So I think it's pretty straightforward. You can, if you think you can integrate what's inside the sum, go ahead. You can show that it's divergent or converges, then awesome. Sometimes the things inside the sums can't integrate them. They're a little bit weird, or maybe there's a better way of doing it. These two are perfect examples of actually doing the integral test. So this actually kind of comes together with what we were learning before, is p-series. So what is a p-series? It is the sum that goes from 1 to infinity of 1 over n to the p. And if you remember, this looks a lot like the integral, but like the p integral back from a few sections ago, where we had the integral from 1 to infinity of 1 over x to the p. And if we know that we know which ones of those converge, right? And that means we know which ones of these converge by the integral test. So this is convergent. If p is greater than 1, divergent, if p is less than or equal to 1. Right? So remember this, because this kind of brings in our next test, which we can use a lot. And I'm actually going to go to the next page for this. We got some room. We're going to be talking about two tests here. The comparison test So what is the comparison test? Well, let's say that we know something about the sum of the Bn, right? This guy is known. It's known to converge or diverge. We just know something about it, right? If this sum converges, and we have that some sequence of an is always less than bn, we have that the sum of an converges. Right? So this is kind of like the comparison test for integrals, right? If all of the terms in an are less than bn, and the sum of Bn converges, then we know that An converges because it's less than it, right? We have to make sure that these terms are always going to be positive or negative. They can't just keep flip-flopping back and forth because otherwise there's nothing bounding it from below, right? So as long as it's bounded between 0 and Bn, then we're good to go. This extends, just like the comparison test for integrals, if the same sum diverges instead. And now we've got that An has to be greater than Bn. That means that this sum diverges. So again, it's really important to understand the ordering of these. If we've got a convergent Bn and we have that An is less than Bn, then An converges. And if Bn is divergent and we've got that An is greater than Bn, then the sum of An diverges. So a lot of mistakes that I see are flip-flopping. Let's say that they say that they can show that something, they don't have this right. They have that An is greater than Bn, but Bn converges. That doesn't mean that An converges. It just means that it's greater than it. So just kind of think about which way you're applying this. Remember, if you want convergent, you want something that's smaller, right? You want something that's smaller than the thing that you know that converges. If you've got something, you're trying to show something diverges, then show something bigger than it, or smaller than it diverges, right? So remembering the order behind these is really, really important. I see a lot of mistakes early on with the comparison test. So our next one is called the limit comparison test. Right, the limit comparison test. And what does the limit comparison test say? We have that the sum of An and the sum of Bn are two things. So one of them we're trying to show is convergent or divergent, and the other one we know, right? We also have the condition that An and Bn are both positive, right? So all the terms are positive in both of these things. So if the limit as n approaches infinity of An over Bn is equal to C, where C is bounded, so it's finite, then we have that the sum of An and the sum of Bn both converge or diverge. So what exactly does this mean? This means if we want to know something about the sum of An and we know something about Bn, we can do the limit comparison test, and if we get a finite C, then we know they both do the same thing, right? So let's say I know that Bn converges, and I test A of n through the limit comparison test with Bn, and I get my limit is a finite thing. Because Bn is convergent, and I know that An is convergent because they both have to do the same thing. If Bn diverges and I test it with An and I get a finite thing, then they both diverge. So we've got our example problem, number 7. we're going to try to fly through this one, run out of time. The sum from 1 to infinity of n over n squared minus cosine squared n. Let's kind of just jump right into it. I've got that we've got n squared minus cosine squared of n is always going to be less than n squared, where n's are integers, right? So what does this mean? On the next line here, we can write that n squared minus cosine squared of n over n still less than n squared over n. So I just divided both sides by n, totally fine. So now what I'm going to do is flip-flop them. So if you invert them, the equality sign gets flipped, which makes sense, right? If you take the numerator on one side, make it the denominator on the other side, and you keep flip-flopping these things, you'll get the opposite is true. We'll get that n over n squared minus cosine squared of n is greater than n over n squared. And n over n squared is just simply 1 over n. Now, what do we know about the sum from 1 to infinity of 1 over n? Well, it's a p-series, right? This diverges. And if this diverges and it's smaller than the thing that we have above, then we know that our sum from 1 to infinity of n over n squared minus cosine squared, this guy diverges by comparison test. All right, so that we're about out of time. So I'm going to be hosting Silva's office hours tomorrow. So make sure you can come and join me. We have our exam next week. I would definitely start reviewing a lot of the material, do some practice problems in the book. You can also find practice problems online. So go ahead, study up, start studying for this exam. And then I will see you guys next time.